hidden inside every curl of smoke, every ocean wave and every drop of rain, is a set of equations nobody fully understands. They are called the Navier-Stokes equations. They describe how every fluid on Earth moves. Water, air, blood, even clouds of interstellar gas. But here is the strange part. We still don't know if these equations always make sense. So in the year 2000, the Clay Mathematics Institute made an offer. 7 problems, $7 million. And one of them is about flowing fluids. Prove the equations always behave, or prove that they can break. And $1 million is yours. This is the Navier-Stokes Millennium Problem. So what do these equations actually say? Picture the air filling this room. At every single point, the air has a velocity. A tiny arrow, how fast and which way. Mathematicians call this a velocity field. Follow the arrows and you trace out streamlines. When the lines glide along in order, the flow is called laminar. But push the fluid faster and faster, and order shatters into chaos. This is turbulence. Same fluid, same equations. Completely different behavior. And Navier-Stokes must govern it all. Here it is, the star of the show. It looks terrifying, so let's take it apart piece by piece. This first term is acceleration. It measures how the velocity changes from moment to moment. This second term is the troublemaker. It is the fluid carrying itself along. Velocity transporting velocity. That single feedback makes the whole equation nonlinear. Over here, pressure differences push the fluid around. The fluid streams from high pressure towards low. This term is viscosity, the fluid's internal friction. It smooths sharp differences away, like honey resisting a stir. And finally, outside forces, usually gravity. And one more rule rides along with it. The fluid cannot be squashed. Whatever flows in must flow out. Put together, this is simply Newton's second law, written for water. So what exactly wins the $1 million? Take a fluid and start it off perfectly smooth and gentle. Now press play and let the equations run forever. Here is the entire question: does the flow stay smooth for all time? Or can it blow up? Blow up means that somewhere in the fluid, the speed races towards infinity. A singularity appearing in finite time. Now in flat, two-dimensional flows, we already know the answer. They stay smooth forever, that was settled decades ago. But in our three-dimensional world, nobody knows. Prove that smoothness always wins. Or construct one single flow that breaks. Either answer takes home the prize. So why has this problem resisted every attack for over a century? Watch what turbulence does to energy. Big whirls carry the energy first, then break apart into smaller whirls, and smaller ones smaller still. Energy cascades downwards to ever tinier scales. To tame an equation, mathematicians need control. Energy is their main handle. But in 3 dimensions, that handle is just too weak. Zoom in far enough and the estimates simply lose their grip. And it gets worse. 3-dimensional flows can stretch their own vortex tubes. Stretching makes a tube thinner, and spinning fluid that gets thinner spins faster. And faster spin stretches the tube even more. It is a runaway feedback loop that flat 2-dimensional flows simply cannot build. Could that loop run away to infinity? That is the heart of the problem. Now it isn't all darkness. Here is the scoreboard so far. 1822. Claude Louis Navier, a French engineer, writes the equations down. 1845. George Stokes puts them on solid mathematical ground. 1934. Jean Larrey proves that blurry average solutions always exist, rough spots and all. 1982. If singularities exist at all, they must be vanishingly rare. 2016. Terence Tao shows that a modified, averaged version of the equations really can blow up. And 2025, artificial intelligence joins the hunt, finding brand new candidate blow-ups in cousin equations. And the true equations themselves, still standing, still unsolved. And yet, engineers trust them every single day. Weather forecasts, aircraft design, ocean currents, computers simulate them beautifully. But a full proof needs something genuinely new, perhaps a whole new mathematics. And maybe, just maybe, that idea is yours. $1 million is waiting. If you enjoyed this, subscribe for more impossible problems.